Okay, first I have to thank the organizers and the committee to include this highly controversial topic to our discussion. So before the PP5, I was a student, and it was a difficult time for me because on one hand, I kept on reading those theories from Frank Shu in the textbook, but on the other hand, I remember I'm sitting in lots of the colloquiums where the speakers would pretty much just give a beautiful map like this, right? And cite words from Frank and cross away the B field and replace it by turbulence. Well, actually, I can totally feel that when I see this figure, I can feel turbulence inside. Yeah, I'm convinced. But what I'm puzzled is I cannot feel where the B field is important or unimportant just by looking at this kind of a fluffy map. So, my purpose of this talk is very simple. I try to visualize the field morphology, right, based on the recent survey of magnetic field. Right, for example, particularly I want to tell whether the field of the molecular cloud is closer to this very tangled scenario or closer to the right-hand one, which has a well-defined mean direction. I think this is an important question to solve because people have no idea about this almost at any scale. For example, for the cloud formation scale, right, if you assume the B field energy is significantly lower than the connecting energy, and this is the result, right, you will find that the B field morphologies pretty much follow the cloud rotation, okay, and be random. Right? On the other hand, if you assume the two energies are comparable, then the magnetic field tension will stop or hinder the cloud rotation, such that the field inside the molecular clouds is only twisted a little bit from the orientation of your spiral arm. When we get inside the molecular cloud, the picture is as controversial because people don't know whether inside the molecular cloud the turbulence is subavionic or supervanic. And the very clear effect of these two parameters is that is the field orientation. Right? From a subavionic cloud, you will find a quite ordered field orientation with well-defined mean direction. On the other hand, a supervanic turbulence will randomize the field orientation. And if you look closer to this density structure here, I would say find this in this map, the density are more filamentary. And moreover, these filaments tend to be either aligned with the B field or perpendicular to the B field. I don't think it is the effect of this particular simulation because I keep on seeing the same thing from other simulations when the turbulence is assumed to be a subavionic, like these two examples here. This one shows a filament structure or condensed structure perpendicular to the B field. This one aligned with the B field. Getting closer to the star, right, the picture is also very controversial of the role played by B field in disk formation. Right, this one again suggests the B field can channel the formation of the disk, while in this simulation, this B field shown by the white line here is not as important. And the orientation of the disk will have nothing to do with the mean field direction of the core. So in the following 30 minutes, I will try to compare the observation with these different simulations. I will start with introduce some of the observation tools of the surveys I will talk about in this talk. Basically, there are two types of tools people use to tackle magnetic field. The first one is related to the dust grain being aligned with the B field. The spinning dust grain will have the longer axis aligned perpendicular to the B field, such that if you observe the polarization of the thermal emission from the dust, they will be in the long axis directions, which is perpendicular to the B field. If you observe the background starlight, which has been absorbed more by the longer axis, the residual will be polarized aligned with the B field. Another type of tool is related to Zeeman effect. Through the frequency splitting of the different circular polarized line, we can estimate the B-field strength, but only the line side component. Also, Zeeman effect will be linear polarized. Right? If you cannot resolve the splitting lines, which is very likely the case for cloud, where B field is very weak, and you observe the polarization of 3 of them together at once, you got the polarization either parallel or perpendicular to the B field. It's also called the Goldrich-Killifish effect. So you probably can tell from now why I choose to use the field morphology to tackle this problem, because it's extremely difficult to get the absolute strength of the B field. Okay, let's start from the larger scale. If you want to put constraint on these two competing scenarios, I'm very simple-minded. I just want to go observe the field morphology. Right? But for this particular case, you have to find a cloud from a somewhat face-on galaxy in order to see the effect come from galactic shear, for example, which would introduce the angular momentum for cloud rotation. Well, the problem is there's no available telescope to see the first kind of tools from an extragalactic source. So if I want to know some idea about the field morphology, I start with only this method. I mean, people think it's not quite useful, right, because it gives you 90-degree ambiguity. But for this purpose, it might be still useful, because assuming the intrinsic field morphology is like this one, it's quite random, and you introduce some 90-degree ambiguity, what you got is still a random distribution. On the other hand, if the B field is quite ordered, right, like a Gaussian type of distribution for the angular, if the direction of the B field, you add in this 90-degree ambiguity, what you got will be a double Gaussian distribution with the two peaks, roughly separated by 90 degrees. Right? So the result will be different, even with the ambiguity. So this is exactly being tried with the clouds from M33, which is the nearest somewhat face-on spiral galaxy. You can see the beautiful spiral arms from this optical image. The vector here are from polarization for synchrotron polarization data, which only show the B field morphology from the low density region, from warm to hot media, which has nothing to do with the cold, dense molecular cloud. So we tried this CO polarization to observe that from the 6 most massive clouds in M33. The reason that the most massive is picked because you have stronger signal, right? Because the degree of polarization is very low. You need a stronger signal to observe, to make observation easier. Here shows here the grayscale is the intensity of the CO 2-to-1 dimension, and the red vector showing the polarization of these CO lines. If you just stare at these red vectors for a while, I don't know if you can see something. I cannot. But if you simply compare the offset between the red vectors and their local spiral arm orientation, which shows by the thick vector here, you'll see something I just mentioned a few minutes ago. So the offset between the CO polarization and spiral arm directions have this double Gaussian distribution, with a tendency for the polarization to be aligned with the spiral arm or perpendicular to the spiral arm. And this, I think, you cannot get from the simulation assuming very weak B field strength, but rather it's consistent with this scenario. So, but it's only suggestive. So I'm thinking if there are other ways I can test this scenario. The one thing we can try is, you can see during this scenario, the gas accumulation must tend to be along with the field line, right? Because there's no magnetic force field in this direction. And only when this accumulation has reached some critical Coulomb density such that the self-gravity can overcome magnetic pressure, then this compression is possible to happen in all directions. Right? Then the field line will start to be compressed. So let's see if we can test this scenario with the Zeeman measurement. But now you have to know that now the Zeeman measurement I'll get from our own galaxy, not from M33, but I think it still can test this scenario. Here, the Crutcher almost collect all the attempts to measure the Zeeman effect. I say attempt because you can see lots of them are not detections. Look at the error bar, there's a very large error bar here. So these are a line of sight B-field trends plotted over against column density. So we have to think twice when we try to interpret this dispersion here. Because first of all, these are only one component of the B field. So the projection effect can easily produce this dispersion, even if they are real detections. Well, second, the other effect which can bias this detection here. For example, more and more people have been noticed that you might have the field direction reversal inside your beam, and this will bias your field trends toward the lower end. Well, we have a detailed discussion about this in our paper, but for now, I would just take the safest assumption, which will be that only the upper envelope of this distribution will give us some idea about the total B-field trends, right? Because the projection will all lower them down, so the upper limit should be closer to the total B-field trends. And I think it's not hard to notice that this upper envelope is quite flat in this intercloud medium and start to increase at some point with the molecular cloud. And I think this is another thing consistent with the picture that the mass accretion is first tend to be aligned with along the field direction, right? So the accretion here will not compress the field lines. So the total field strength will stay constant. And based on the data distribution here, Crutcher et al. Concluded that the most probable total field strength from this data is between 6 to 10 microgauss. Given this strength of the B field, you can theoretically calculate what's the minimum column density you needed for stable gravity to overcome this magnetic pressure and collapse and compress the field line. So here, dashed line is the theoretical calculation. So you got the so-called magnetic critical column density. But in order for the cloud to collapse, don't forget that we also have turbulence. So if I assume the equipartition condition between turbulence and the B field, we got another theoretical line for this critical density. So which tells us that if the accumulation along the B field reached at this point, then the gravity just take over, right? Gravity doesn't need the help from either turbulence or before diffusion in order for cloud to collapse. It will collapse just because of the gravity. And it also looks very close to the turning point of this upper envelope here. And we also have other empirical indication of the critical column density for cloud contraction. Right? So I think this would be very interesting to compare with those empirical thresholds. So this is the semi-theoretical value based on the observed B-field trends. So what is the total empirical value we see? So this is the log normal distribution of the column density PDF. We heard a lot from the previous talk. So I learned from the paper of simulation that if you have a turbulent cloud, right, then your column density PDF will be log normal on the density regions. But for the regions which reach the column density such that the stable gravity is strong enough to make the cloud contraction, for those column densities, the distribution will deviate from this log normal distribution. Right? So in this sense, you can take this turning point as a critical column density for the gravity stable gravity to take over to collapse. And Carolina et al. This is not a simulation, by the way, this is observational data from the nearby clouds in the Gold Belt. And he found that this turning point is mainly distributed in the greenish zone here. And I think it's very close to that purple region, which is defined by the B field strength. So I think, so far, I think we see from both the morphology point of view or B field strength point of view, we see B field can play an important role in cloud formation. Next, I'm moving to inside molecular cloud. So first, again, I want to visualize what the real field morphology is, right? Because we want to look inside the cloud, we have to come back to a Milky Way where we can get higher spatial resolution. And in the Milky Way, we can use these two kind of a technique. But you probably notice that they also have very large limitation here, again, mostly due to the sensitivity of our telescope. So I would say for this kind of limit, you can only see mostly the B field in the intercloud medium, or maybe the low-density part of the cloud. And from the other technique, you only see the B field from the cloud core. So that this will leave the bulk volume of the cloud is still invisible in the sense of the field morphology. But I would say if, for example, this picture is indeed what is happening, then we should expect there's some orientation correlation between the B field from inside the core and the B field even outside the molecular cloud, right? If this is indeed what is happening. So the first cloud I want to try is Orion, because it's a popular example to show how turbulence is important, right? But what's the B field from here? So these are field orientation inferred from the starlight polarization, which probe the low-density region. I would say they are not random, right? Actually, they are quite ordered with a well-defined mean direction here. And if I look into the dense core in this region, for example, is core C and is NGC 2024, again, with the polarization of thermal dust emission, we see quite ordered B field directions, which is perpendicular to the elongated core, and then most importantly, the field of orientation is quite close to the mean direction from the low density region. Recall that they come from very, very different density. And core C is not just a special case. Actually, here I show all the cores in these regions, right? The red vectors come from the polarization of thermal dust emission, and the inferred mean field direction shown by is white vector. And you plot all these mean core field on this map, you can see the white vector are not too far away from the mean density, even come from outside the cloud. And we can do this test to all the clouds where the thermal dust emission polarimetry is available from the core and optical polarization is available from the surrounding intercloud media. And this is what we got. I think it's quite a close correlation here, which means the B field in between cannot be very tangled. Okay. Given the cloud B field so ordered, then we should expect some of the density structure we see from the simulation, right? Again, recall that if the B field is ordered, in the simulation we see an elongating structure either aligned with the B field or perpendicular. And let's take a quick look at Orion. To do a very old-fashioned way here, I just highlight those high-density zones, right? Those green zones are having the intensity of 100 micron emission above 20% of the peak value of this map. And immediately I think, I don't know about you, I can feel something is not that turbulent because I see some elongated structure, right? They're parallel to each other. And moreover, the orientation is close to be perpendicular to the B field. You can ask, what kind of other mechanism can give you this parallel density structure? Right? Probably not stellar feedback, not superbaric turbulence. Again, we can apply the same technique to all the nearby cloud, where we can get the B-field orientation from optical perimetry data. Right, here are just some examples that optical polarization is shown by this grayish cone here, show the range of the polarization. And then we can use the extinction data to study the cloud elongation. Well, you can even tell by eye that you have got some elongation direction, right? But here, the dotted lines are the direction where the map has the longest autocorrelation length, which has been used as an approximation of the cloud elongation. For some cloud, you can notice that it depends on which density you are talking about. The elongation might vary, right, from the low density filament to high density to other directions. So if we put together these two directions in a plot, this is what we got from almost all the cloud along the gold belt. Right? All the cloud, we have optical perimetry data. And in the x-axis, of course, this arrow bar showing the range of this cone, the range of B-field orientation. And in the y-axis, the arrow showing how the cloud orientation varies from low density to high density regions. And I think they have the tendency to concentrate along either align with each other or perpendicular to each other. All of them have this offset only 30 degrees, within 30 degrees from perpendicularity or parallelism. And 90% of them are within 20 degrees from these two lines. And to get this kind of distribution from random distribution, the chance is 0.6%. So we see some tendency of B-field controls the orientation of the filament. How about further fragmentation? How about cloud core? Cloud core could be trickier because they are not always as elongated as filament. So in this case, you can define the mean elongated directions, right, which goes perpendicular to the B field. And this one is completely roundish. It could mean that the B field is not so important here, so gravitational contraction is isotropic. But you also see a very ordered field orientation. Right? It doesn't look like to be dragged toward the center very much. So Tessis et al. 2009 has another idea. They proposed that the shape of the cloud core is more oblate, right? Because the B field is still strong enough to affect the contraction of the cloud core. Right? So it contracts more along the B field, but less perpendicular to the B field. The result is like these toys here. But it's hard for you to always observe this kind of morphology, right? Because sometimes you will have a lamp sight close to be face on. Then, like this one, you are going to see any correlation. But if this is indeed true, then you should expect the alignment between the short axis and the B field to increase with the projection elongation, right? The more elongated the projection, the more alignment you should find. And they studied about 30 cloud core and claim that they indeed see this kind of a tendency. So here, the x-axis is the ratio between the short axis to long axis. So the more to the left, the more close to the edge on. The y here is the offset between the B field and the short axis of the core. They claim there's a tendency here decreasing. And they also calculate the chance to get this kind of distribution from random is about 1%. Okay, so I think, again, we see some effect of the B field, right? Because we see some tendency of the orientation of filament and cloud core related to the B field. So my last topic will be how about B field in disk formation. Talking about disk formation, I cannot help to think something similar about the cloud formation, because in both cases, right, if you want your gas to rotate, right, form a disk, you have to rotate, right? You have to overcome magnetic tension force. Right? Just like when you form a cloud, you have to do the same thing. You have to overcome magnetic braking. But based on observation, at least for M33, it seems not the case, right? The cloud angular momentum is not big enough to twist it to field lines. And compared to the observation for the disk formation scale, we also observed the very ordered B-field orientation. And if you recall that a Zeeman measurement plot I show, you'll find that the B-field strength here is in the order of microgauss. The B-field strength here is in the order of milligauss. So you should expect a stronger magnetic braking at this scale. And yet, if your angular momentums come from galactic shear or turbulence, right, if you have the same angular momentum source here, you got smaller this kind of energy because there's no galactic shearing here, and based on Larson's law, turbulence velocity is much smaller here. So then there's a mystery that how you cannot make a cloud rotate, but you can make a disk rotate under the magnetic braking force. I think Jirin Li will give lots of different models to get around of this problem tomorrow. And today I just want to link one of the observations which might shed some light on this problem. Because first I asked myself to get a very efficient any brake, right? Doesn't have to be magnetic brake, any brake from your car, right? You have to have your brake well coupled to the things you want to brake, right? Which means here you have to make sure your field line is well coupled with the gas, so it can stop the gas rotation. But can we just simply assume so for all different scale? I don't think so. This is what the induction equation teaches us, right? The equation says that only when this magnetic Reynolds number becomes very large, so you can ignore this diffusion term. So everything will be decided on this convection term. So the gas velocity and B field will act together. So only when this is really big, you can assume you have a very efficient brake then. And you can approximate this ratio by the characteristic scale times velocity divided by diffusivity. I think immediately you see that you really cannot assume the physics at these two scales are the same, right? Because you got the scale here. And moreover, if the velocity is mainly due to turbulence velocity, it will decrease with the scale. Right? So you can expect at some scale, your B field has to be decoupled from your turbulent eddy. Right? And then you no longer have as efficient magnetic brake for turbulence as you have at a larger scale. So now the question to ask is this scale comparable to the disk formation scale? I think there's a way to observe this decoupling, which is if you can observe the turbulent energy spectrum of neutral and ion, right, we should expect the ion to be better coupled with the B field, which means the ion and neutral should be decoupled. And how can we observe this? We don't necessarily to go into a scale below this decoupling scale. Right? If you recall that the square of the line width we observed is actually due to the turbulent energy within your beam size. Right? The turbulence energy within your beam size is equal to the integration of this turbulent energy spectrum from the scale of your beam size all the way down to the scales within your beam size. But if you do this integration for the ion line width and neutral line width, of course you should get different value as long as you have this decoupling scale at small scale. It doesn't have to be comparable with your beam size, right? You can have a larger beam size. And When you dig into the literature, you will find that this systematic line width difference between ion and neutral is discovered by Martin Wu in the early 2000s. Just Martin Wu et al. Doesn't then connect this phenomenon with the induction equation. But I think induction equation can really explain this systematic line width difference. Like here, you have this line width difference measured from very different column density, but very ordered field strength. By the way, the grayscale is column density. The white line are the field lines. Right? So regardless, it's very different column density, got very similar line width difference. And this example is more interesting to me because for NGC 2024, we have a very good idea about the B field strength based on a Zeeman measurement. And you can see for the region, now the color is not column density, the color is the B field strength. So for the zone with strong B field strength, the line width difference between ion and neutral is very large. And for the zone, almost have zero B field strength, you almost find no line width difference between these two components. And if you assume this is indeed what is happening, well, you can use this line with your line measurement to estimate this turbulent energy spectra, and use this line width difference to estimate the area of this shaded region. And you put these together, you are able to estimate this decoupling scale. It's just from a handful of clouds we observed, we find it's in the order of 100 AU. So I think this means that one really shouldn't assume that the magnetic braking is as efficient at small scale compared to at larger scale, both from theoretical point of view and from observation point of view. But this is not good enough to put constraints here, because I think this decoupling will help both the cases. So as the last topic of my talk, I want to introduce some recent observation which is able to, well, they claim this might be able to put constraints on that two disk formation scenario. Well, this looks a little bit different from what I prepared, but you can see probably from what the rest here, from this observation, they find that B field orientation shown by the red vector tend to be perpendicular to the disk. This is just a recent released survey of core field orientation versus the disk orientation. They're doing this using the CSO, so for each map, the size is about 10,000 AU. Another survey released about the same time, but they use a comma to reach much higher resolution, and they find the opposite result. In this scale, they find the polarization data is not correlated with the disk formation. They're almost random. So this makes the kind of support a different kind of a scenario of disk formation, right? But how can this be possible? I find an alternative explanation for this different observation. I use another simulation to try to illustrate this possibility. Here is another strong B field scenario of disk formation. So the disk is formed perpendicular to the B field. And here I just show the different scale from the same simulation. When you observe with a line of sight 45 degrees from the B field orientation. And then again, you see that at the larger scale, 10,000 AU, your field orientation, showed by this dark vector here, tend to be perpendicular to the disk. On the other hand, when you zoom into the central 1,000 AU scale, you start to see the B field orientation all over the places. They almost look like loop. Right? But the reason is, 1,000 AU, you start cutting to a scale where the field morphology gradually changing from poloidal of the core field to toroidal of the disk field. Right? This is field morphology created by the disk. So you no longer see the B field from the core. Right? So I would say the result here is probably not good enough as an interpretation of the core field and disk alignment. So it's almost all I want to say. As a summary, I think I show some evidence to you that the galactic B field orientation is preserved inside the molecular cloud and all the way to the cloud core. And we also see the consequence that you should expect from this kind of field morphology. For example, we see the orientation of a filament and core to be correlated with the field direction. We also see that magnetic critical column density is very comparable to the empirical column density of cloud contraction. And as for the B field plays in disk formation, I would say more data and more careful comparison between observation and the model are needed. But in either case, I think at a smaller scale, right, the B fields should start to be decoupled from turbulent eddies, and this might have some effect on the magnetic braking catastrophe. I will end up here. Thanks.
Thanks very much. Are there questions? Yes, Roby.
Yeah.
Please identify yourself.
Roby Banerjee.
Hi, Roby.
I'm wondering how much are we kind of tricked by, looking at these polarization maps and picking out only the large-scale component of the magnetic field, even if there would be, say, a small-scale component which might be actually stronger than the large-scale component, as we see, for instance, on galactic scales. Are we, how certain are we that this is the dominant component, the large-scale one?
Okay, thank you, Roby. I think you are probably asking about, maybe I can restate your question. You are saying, like, here we have a larger scale field morphology, and when I try to observe the smaller scale, like from the core, maybe I was biased by the larger scale B field. Is this what you mean? Yes, it's from observation. Yeah. Well, one of the explanation is that as I showed that those optical data, right, only sensitive to the very low column density, so A sub V less than 5. And the polarization we got from the core is from A sub V several hundred, even thousand. Right? So even if you assume that the polarization from the low density region is 100%, you overlapped this 100% from 5 A sub V equal to 5 magnitude to A sub V equal to several hundred, you got almost no polarization. But still, from the cloud core, we also got a few percent polarization, just like what we got from the low density region. So this can be one of the explanation why we are confident about we are reading probe in the core. Well, another explanation is now we observe the same source with single dish and with interferometer. When you observe with interferometer, you fill out most of the foreground and background, right? And you really dig into the center to the core. And for many cases, we still see the same field orientation. In other cases, we see from the interferometer, we see from the core, we see the effect from stellar feedback. Right? This really makes us think that it's really dig into the core. Otherwise, you won't see the stellar feedback. You won't see this effect from the small H2 bubble from deep inside the core. So
There is a question up there.
Yeah, I'm Paolo Padoan, University of Barcelona.
where are you?
I'm up here. I'm up here.
Oh,
Yeah.
okay.
Hi. I think it's a continuation because I don't think I understand the answer you just gave. It's well known that there is a strong reduction in the polarization degree inside the dense cores. So there are two obvious explanations. One is that the field is tangled in the core, and the other one is that the degree of polarization drops in the core because if you need radiative torques and you don't have enough radiation for the grains to be aligned. And so, but if you assume, number one, that you are sampling the field inside the cores for some reason, because maybe you have enough radiation, I don't know. Number two, that the field is strong and therefore not tangled, then you have none of the two options available to understand the drop in the degree of polarization in the cores. So what is the solution to understand that?
Yes, we have a solution on this. First, is usually we see what you call this polarization hole, right? I hope I have here it can be an illustration. Here, unfortunately, I plot all the vectors the same length. If I plot all the lengths proportional to the degree of polarization, you will see something Paolo just described. You will see the degree of polarization decrease, kind of decrease with the column density. Right? To explain this, I want to bring another two observations. Right? One is, if you observe, you don't observe this, you don't try to correlate with the degree of polarization with column density, and you try to correlate with the degree of polarization with the line width, and you got an even better correlation. I think this explained that it's similar to the Chandrasekhar-Fermi relation, right? When you have a larger line width, you have larger turbulence, so you expect more structure of your B field. So this will decrease your degree of polarization. Right? Not necessarily tangled, only more structures from, for example, you have a larger line of sight, which will give you a larger line width. It will take the mean over from its larger line width, so of course you've got a smaller degree of polarization. Another observation is, if you observe like, say, 2% from the core, and you zoom in with the same position with the interferometer, you got larger degree of polarization. This is consistent with the previous observation, because with interferometer, you fill out the foreground and background. So you only concentrate a shorter scale of line of sight. So you get less dispersions from the line of sight. Then you got a larger degree of polarization. If the grain is not aligned from the core, then you shouldn't see this larger degree of polarization. So these are the two observations, I think. We also have this discussed in our 09 paper about these different possibilities.
Hi, Jonathan Tan. So very nice results. I'd like to understand in a bit more detail whether you think clouds are sub or supercritical based on what you showed when comparing to de Crutch's fields. As I understand it, you're basically saying if you account for the extra support due to turbulence, which is present in the clouds, then the observed field strengths are just about at the level they need to be to, where you are on this sub and supercritical boundary. Is that a fair
Yes, I think when you over that threshold, I think the cores are all very close to critical.
Okay, so then my sort of follow-up from that is, what are your thoughts on creating the initial mass function or the core mass function from a range of magnetic field strengths to produce different masses of cores?
This I don't know. You mean how the IMF can be decided from the B field strength? Right? So this I don't know. Maybe the strength of the B field. But how they can produce that spectrum, I don't know. For me, I still think that the spectrum is very close to turbulence. So that's why I always think both are as important. Even if you have very old B field, still along the B field direction, you have free turbulence. And with or without strong B field, simulation always show a log-normal distribution of the column density, and also show that deviation from the tail from the log-normal distribution. So this property only introduced by turbulence also see in subaventic turbulent simulation. So I think the effect of turbulence is always there, regardless of the strength of the B field.
Last question.
Yes, Chris McKee. Actually, this is just a comment that's relevant to the first question. As you probably know, Paolo Padoan and his group have done a lot of simulations which show excellent agreement with observation when you start off with a weak magnetic field and allow it to be amplified by turbulence, which is the opposite of the picture you're giving. And in simulations we've done, we've confirmed what he found, but we find that only when we assume an initially strong magnetic field do we get a correlation between the field on the small scale and on the large scale. So that's sort of observing by computer.
Okay. First of all, I think, yeah, this indeed did not agree with the large small scale correlation I show. But on the other hand, I think you agree with the small scale B field. Are you talking about the agreement with the observation from big quadrature about the ratio of R smaller than 1?
Yeah, we got very good agreement with quadrature.
Yes, but on the other hand, I want to point out one simulation done from here. I think it's from Beltram, from the ETA. They got this also the same result, similar result from subavantic simulation. Because I think the point is, in order to get the field reversal, you don't need really to tangle the B field. Right? Like if I arm is the B field orientation, and you observed the B field have some structure in this orientation, you don't see any orientation reversal in one dimension. But if you change the line of sight, now you see the reversal. So this is the way, at least for me, to understand why the subavantic simulation from Beltram et al. Can also reproduce the quadrature result if you don't do this alone, the line with B field, but have a line with size not aligned with the B field, you can see the same effect, the field reversal effect.
Thanks very much again.